Okay, so this is the uh, help session for lab 4.1, where the assignment was to build a 5-second turnoff delay. And what I'm going to show you here is a 10-second turnoff delay. So the only difference between what I build here and what I've asked you to build in the lab is the amount of time that the LED stays on. So the idea behind this circuit is you have a switch, and when you press the switch, you're going to quickly charge up a capacitor. It's going to happen very quickly, about a tenth of a second. Then you take your finger off the switch and the capacitor is going to discharge. And we set a fairly long time constant on the discharge. And the result is that an LED at the output of a comparator is going to stay on for 10 seconds. Okay, so let's just talk about the circuit and the way it works. Um, Working from the LED backward, the LED is at the output of a comparator. So that comparator output is high or low. We see that the comparator is going to be connected to a 6-volt rail and a 0 or ground rail. And so we have two inputs. We're going to have the input from our charging and discharging RC circuit. That's on the V plus input. And then on the V minus input, we have this node here, which is a voltage divider, where we have our 6 volts, a 3K, and a 1K resistor. And that's going to give us 1.5 volts right here. So what's going to happen then, due to the RC action over here, whenever this voltage is above 1.5 volts, we'll have a high here and the LED will turn on. And when this voltage is below 1.5 volts, this will go low and the LED will turn off. Okay, and so how does this circuit give us a value here that's greater than 1.5 volts for 10 seconds when we want it? Well, it starts out with this switch, and this is a momentary contact switch. So take a look. You have our 6-volt battery here. Notice that that's just connected to the positive voltage rail here on our breadboard, and then all these triangle symbols represent the ground rail on the breadboard. Okay, what we're going to do is notice that I have an RC circuit here, and notice that I have R1 is 10K, and then the capacitor value is 10 microfarads. So the time constant, R1 times C, is going to be 0.1 second. So it's a fast time constant. So what will happen is when we close that switch, this capacitor will charge up to 6 volts or close to 6 volts in a couple tenths of a second. So the idea is it's a momentary contact switch. Press it, the capacitor quickly charges up, then you take your finger off of the circuit. It's no longer connected to the battery, and what's going to happen is it's going to start to discharge through this part of the circuit. Now, the op amp has a very, very large input resistance, so we can ignore any current pulled by the op amp. So what happens is once the capacitor is charged, it's going to discharge through this resistor here. This resistor, we've chosen a value of 832K. Now you can go back and look in the notes from lecture number 25, and you'll see how we came up with that particular value. The idea here is that the time constant associated with the discharge, R2 times C, that's 832K times our capacitor, 10 microfarads. This gives us 8.32 seconds. And so we did work through the discharging math so that it's going to take 8.32 seconds. Well, that's the time constant of that circuit. And the result of it is that once this is charged up to about 6 volts, it's going to actually take a full 10 seconds before this voltage dips down below 1.5 volts. So the result should be an output pulse here that's 10 seconds long, and the LED should stay on for that amount of time. And again, I refer you back to lecture 25 for the actual mathematics behind this. Just a little bit about the components we're using. So the capacitor that we'll be using is going to be a 10 microfarad capacitor. You have two different types of capacitor in your kit, a big one and a little one. This is the big one here. Then the small capacitors look like this. So the big one is 10 microfarad. The small one is 0.1 microfarad. They happen to be two different capacitor technologies. This one's called an electrolytic capacitor, but for our purposes, it's just the large value that we need here. And we needed that large value because we want a fairly long time constant here. You'll be using the smaller capacitors to create tones and blinking LEDs in the next part of the lab. Okay, one more thing about this capacitor. As an electrolytic capacitor, it's polarized. So that just means that when you hook it up, you want to make sure that you get the positive polarity on the correct side, negative polarity on the correct side. And it has a little minus sign on it, which points to the lead, which should be our ground, and the other one should be our positive voltage. Okay, we're also using a new resistor here. We're using a variable resistor, and the schematic symbol is a resistor with a diagonal line through it. And here's what that looks like. You'll see that it has a screw on the end. It's a small slotted screw that you can use for tuning it. And then you need a tool like this. That's a potentiometer trimmer or a pot trimmer, and you can use that. It fits right in there, and it'll adjust by turning that, and it takes about 15 turns with this device to change the resistance from a megohm all the way down to 0. On the top of this, if you read it, you'll see it says 105. So it's a 105 potentiometer. The 105 refers to the multiplier of 10 to the 5th. So this 105 potentiometer has a maximum value of 10 times 10 to the 5. So that would be 1 megohm. So you can adjust, the way this works is you're going to have a fixed resistance of a megohm between this terminal and this terminal, between the end terminals. Then you can vary the resistance between the middle and the two ends, such that the resistance between these two plus the resistance between these two will always add up to a megohm. Now, the way we're going to use it in our circuit is we're going to use the resistance between the middle and the endpoint farthest away from the screw on it. And I'll show you once we build the circuit why we're doing that. The reason is I want to be able to have this installed in the breadboard, and I want to be able to sort of get a clear view to adjust that screw when we need to. Okay, so let's go ahead and start to assemble this circuit on our breadboard. So the very first thing I'm going to do is just power up the LED, and I'm sorry, power up the op amp. And just to remind you, on the drawing here, I've shown the pinouts. So for our op amp, pin 8 is going to go to VCC, which is 6 volts. Pin 4 is our minus VEE, that's the negative voltage supply. That's going to go to ground. The output is pin 1, as you see in parentheses. Then the two comparator inputs are 3 for the V plus or non-inverting input, and 2 for the V minus or inverting input. So very first thing is just put our VCC and then our negative battery on there. Okay, and so now I'm going to start building this RC circuit. When we're finished, we'll hook up our battery to the plus and minus rails. Okay, so I need this 10K resistor, and that's brown, black, orange. And I'm going to put it right in here, and I'm going to leave it sticking up in the air. Now, why am I doing that? The way we're going to build a switch is just with a piece of wire here. And since we don't have an actual switch, all we'll need to do is touch that together. Whenever I just touch that, I'm closing the connection between this end of the resistor and our positive voltage rail. So that's how I'm making this switch here. So we have that switch, we have our resistor, and then we're going to go to our capacitor and then to ground. Okay, so what I want to do is I want to keep this real estate on the board available for that variable resistor. So I'm going to put the capacitor in up top, and I'm going to make sure that I have where I have a negative sign. I'm going to ground that, and I'm going to actually ground it to this top rail, or not the top rail, but the second from the top rail. It's a blue rail here. So I've got the very top row, the red, that's going to be my VCC, 6 volts. The one just below it, I'm going to use that as one of 2 ground rails. We've got the bottom ground rail that we conventionally use, but what I'm going to do is add another jumper wire between this rail and this rail. So what I'm doing is I'm extending my ground rail between the lowest row and then this second row from the top up here. That way I can tuck this little RC circuit right in here. Okay, so what I've done is I've got my switch, my resistor, and then the capacitor, and that's this node here. And then I have to connect that to our plus or non-inverting input of the op amp, which is just pin 3. So that goes into pin 3. Okay. And now I have to put that variable resistor on there, and it's going to be connected to this same node, this same node right here. I have to put this variable resistor and then bring it to ground. So what I'm going to do first is I'm going to, outside of the circuit, I'm going to take that variable resistor and I'm going to set it up with my multimeter so that it is our desired 832 kiloohms. So I've got the meter set up, and I'm going to be using the alligator clip leads to do this. Now, I just want to show you something. We're dealing with a very large value of resistance. It's close to a megohm. And we're going to use these two leads to connect to that resistor. And I just want to show you what happens if you just connect your body to those leads. Nothing happens. Well, that's not right. Okay. Here, I'm just going to, what I'm doing here instead is I'm squeezing the probes of the meter. Okay, there it is. So what I've done is I've got my fingers and I'm squeezing the two probes of the meter, and you can see that I have a resistance there of about 600K. If I let back on the pressure and don't squeeze them so much, but just touch them, it's greater than a megohm. But when I do have them connected, when I'm squeezing my fingers, you can see that I have a resistance from hand to hand of about 760K, which is pretty close to the value 832K of the resistor that we're using. And I point this out because I want you to know that your body has resistance. And if you're actually touching the circuit, you could actually change the values of some of the parameters in the circuit. Okay, so let's measure the resistance of this variable resistor here using our clip leads. And it should be, initially it should be about a megohm. Okay, there it is. It's a 1.012 megohm. Okay, now what I'm going to do is I'm just going to use this pot trimmer to adjust it down to 832K. Takes a lot of turns. Okay, we don't need to be too precise here, because if what we could do is once we have this in the circuit, then we could time it if we want to make sure we've got our 10 seconds and then adjust it if we need to. There's our 830, or a little bit more, but that's okay. Now let me show you what happens if I inadvertently put my finger on there. See how I changed that? That's just the effect of my hand on there, getting my fingers in there. So that's why you want to be careful to measure things without touching them. Okay, we've got that resistor now set at the value we want. And it's a little tricky to work with resistors on a breadboard. We're going to use these two terminals, this end and this end. Those are the ones that we just set up. So what I'm going to do is I'm just going to put it in a place on the circuit board where I have some free real estate. And I'm going to note that I'm in columns 24 and 27. 24 and 27. Because we're going to have to, we can no longer see the pins. That's why it was important to note that. Okay, so one end of that resistor has to go to this node where we had our RC circuit, our first RC circuit. And we said we're in columns 24 and 27. So there's 27. Then the other end of that resistor is going to go to ground. So 24 to ground. Okay, so we've just added this resistor into the circuit, and we connected it to this point here, which is already connected into V+. Okay, the remaining part of the circuit is to build this reference voltage here, and then we have to add on our output circuit. So the reference voltage from pin 2 to ground, we have a 1K resistor. And then from pin 2 to 6 volts, we needed a 3K resistor. We don't have a single 3K resistor, but we have a pile of 1K. So I'm going to put 3 of them in series. So from pin 2, I'm going to come up here to some open space on the breadboard with one of those resistors. And then I'll just put another one there. And I'm just going to string 3 of these together to get up to 6, to ultimately get to our 6-volt rail. So that's 2 of them. And then the third one goes to my 6-volt rail. Okay, so now we just have to add the output circuit. That's from pin 1. All right, we're going to go from pin 1 of the op amp through a current limiting resistor and then to our LED. And when you hook it up, make sure that the anode of the LED, that's the longer lead, is connected to the resistor, and the cathode, the short wire, goes to ground. Okay, so that's our LED. The cathode of the LED has gone to ground. All right, the anode is connected to a 1K resistor here. And now we just have to connect that to pin 1 of our op amp. Okay, there it is. So now I'm going to hook up the battery. And if we've done everything correctly, then what should happen is when I touch this little wire to that end of the resistor, the first RC circuit should quickly charge up, and then the LED should turn on. And then after I take this wire away, that LED should stay on for 10 seconds. And I'm just going to count 10 seconds. Ready? Okay, there it is. 1001, 1002, 1003, 1004, 1005, 1006, 1007, 1008, 1009, 1010. Okay, so that's pretty accurate. If we needed to adjust that, I could simply take the screwdriver here or this pot trimmer and I could adjust that variable resistor, but we already adjusted it pretty well. Okay, that's the end of that demo.